All right. So good morning, everyone. My name is Ian Song, and I go by Chris. I'm a PhD student in Pennsylvania State University. I'm going to defend my thesis this fall semester, and my research is about electrical vehicle, including charging behavior, charging station planning, and EV traffic assignment. I think Matt just introduced me. Today, I'm happy to present one of my research, a two-stage demand prediction and optimization modeling framework for charging station location problem. I will introduce this research in the order of introduction, literature review, problem formulation, solution algorithm, case study, and conclusion. So this problem is to be solved in this research is charging station location problem, denoted as CSLP, which is commonly defined as the selection of the optimal locations for charging stations by charging service providers, so that the charging demand of EV drivers could be satisfied to the maximum extent under the limitation of investment budget. Here, the charging demand is equivalent to the usage rate of charging stations. So the objective is to maximize the usage rate of charging stations so that the charging demand of EV drivers can be satisfied to the maximum, and the profit of the charging service providers can be also maximized. This problem is important to solve the chicken and egg dilemma of the relationship between EV adoption and the recharging infrastructures. This dilemma is defined as the lack of penetration in the EV market limits the value of infrastructure investment, which slows the deployment of charging stations. On the other hand, the lack of charging infrastructures present a significant obstacle to the drivers to choose electric vehicle. So by optimizing the location of charging stations, the usage rate of charging stations can be maximized on the limited investment budget. In the literature review part, existing CSLP formulations can be mainly categorized into flow-based and node-based models. Flow-based models assume that the charging demand or the potential usage rate of charging stations can be represented by the covered EV traffic flow on routes between a set of OD pairs. However, the correlation between the charging usage rate of a charging station and the passing traffic volume has not been clearly demonstrated. So flow-based research failed to explicitly model the usage rate of a charging station. Unlike flow-based models, node-based models typically use the size of charging station service area to indirectly represent the charging demand. So in this case, an explicit prediction of charging stations usage is still not available. Another critical issue of current CSLP studies is that they ignored the effect of charging facility supplies on charging station usage. To specify, the deployment of a new charging station may increase or decrease the charging usage of its neighboring existing charging stations. However, such charging demand-supply interaction was not considered by existing studies. To summarize, an explicit prediction of charging station usage and charging demand-supply interactions are needed to be solved in this research. To fill the two research gaps, a two-stage CSLP model is proposed. In the stage 1 model, instead of using the assigned traffic flow or the service coverage area to represent potential charging demand, I use the weekly charging usage rate as an explicit measurement. an ensemble learning model is developed to generate charging demand predictions based on charging event log data, travel demand model data, and climate data. And then in the stage 2 model, a demand supply coupled charging station location selection model is developed with the objective of maximizing the total charging station usage of both existing and newly selected charging stations. The proposed model is solved with a greedy-based stochastic spatial search algorithm and tested by a real-world case study. In the stage 1 ensemble learning model, the target variable is the number of charging events of charging station I on week W. So we have total 15 input features covering spatial context information, weather information, port type, and traffic information. Of the 15 features, the NHCS, which is the density of charging stations in the same zip code area of charging station location I, measured by the number of charging stations per square mile. It is expected to be an important feature because this feature is directly related to the charging station location selection by the stage 2 model, so that in the stage 2 model, I can improve the charging demand by adjusting the number of new charging stations in one zip code area with this feature. So based on the 15 features, I can predict the charging demand, which is measured by the number of charging events per week with the stage 1 model. This is the stage 1 ensemble learning model for explicit charging demand prediction. With the target variable and 15 features at the input, equation 1 is the objective function of the ensemble learning model. It is to minimize the difference between the real value and the predicted value. The first component is the loss component to encourage the model to learn. And the second item in the objective function is the regularization component to avoid overfitting. In equation 2, theta is a set of base regression trees with the total number k. That is, during the model training process, we train one base regression tree at one iteration, and finally total k trees are obtained, which make up the ensemble learning model. And in equation 3, L is the loss function that takes the square loss form. In equation 4, omega is the regularization component. Equation 5, the predicted value is the summation of the regression result of total k trees. And equation 6 is the input feature vector. This is the stage 2 demand supply coupled model for site selection optimization. Here, equation 7 is the objective function. The first component is the summation of the charging station usage rate of newly planned charging stations, while the second component is the summation of the charging station usage rate of existing charging stations. And equation 8 is the trend charging demand prediction model from the stage 1. And equation 9 calculates the density of charging stations in one zip code area. As the equation 15, the decision variable xi is a binary variable. It equals 1 when there is a newly planned charging stations at a location I. Otherwise, it equals 0. By adjusting the decision variable, the charging station density of each zip code area can be increased or decreased, which will further affect the charging station usage by the equation 8. So the objective value can be sequentially adjusted. The stage 1 model can be solved with a given Python package accordingly. So here I will just discuss the solution algorithm for the stage 2. Gradient-based stochastic spatial search algorithm. It consists of 2 major components: stochastic searching set construction and gradient-based spatial interchange. So the basic idea is that starting from an initial solution set S, containing a number of P new charging stations, in each iteration, for a charging station SP in S, first construct a stochastic searching set for it, and then perform gradient-based spatial interchange to identify a candidate site with the highest charging demand improvement. This candidate site will be used to swap out the site SP, and finally iteratively repeat this process until the stopping criteria is satisfied. So in the case study, we use the real-world charging log data collected in Kansas City, Missouri, to validate the proposed model. In the left figure, this is the spatial distribution of existing 444 charging stations. We can find that most of the charging stations are concentrated in the downtown area. The right figure shows the spatial distribution of candidate locations, with each zip code area contains 5 candidate sites. So we have total 355 candidate locations, evenly distributed in 71 zip code areas. In this case, we need to select 50 newly built charging stations from 355 candidates to maximize the total charging demand of the both existing 444 charging stations and 50 newly built charging stations. Here is the training result of the stage 1 ensemble learning model. As shown in the left figure, the R-squared value are 0.72 and 0.63 on the training and testing subsets, respectively. Thus, the model performance is satisfactory in generating accurate charging demand prediction values. And the top 10 most important features with the largest importance value is given in the right figure, with the x-axis being the importance value measured by the mean shape value, which is the average impact of a specific feature on the modeling output. And the y-axis is the top 10 most important features. We can find that the 2 most important features are all traffic related: nearby traffic AADT and trip production. The density of charging stations in one zip code area, NHCS, ranks the 4th, which validates that the charging station usage can be affected by the density of charging stations in the same zip code area. This is the result of the stage 2 site selection model. The left figure is the initial solution with 50 randomly selected charging stations. They are evenly distributed in 50 zip code areas. The right figure is the final solution. We can find the final 50 charging stations are more concentrated in certain zip code areas. For example, one zip code area has 3 new charging stations, and 18 zip code area has 2 new charging stations. In terms of charging station usage, we can find that the colors of charging station in the right figure is darker than that in the left figure, indicating that the charging demand of the final selected charging stations are higher than the initial solution. So this is the solution result of charging demand value. In the figure, the y-axis is the charging station usage value. The x-axis is the existing charging station, newly selected charging stations, and their summary. Each contains the initial solution, the proposed algorithm solution, and the solution of two benchmark algorithms. The first benchmark is simply selecting the candidate locations with the highest predicted charging demand, which is named as naive greedy selection strategy. And the second benchmark algorithm updates the selection only from one adjacent area without the stochasticity from non-adjacent areas, which is named as naive neighbor swap strategy. We can find that when all the charging stations are combined, including the 444 existing charging stations plus 50 newly selected charging stations, the proposed algorithm generates the highest usage rate at 1,459 charging events per week, which can improve the charging usage rate by 14% over the initial solution and outperform the two benchmark algorithms by 2% and 0.5% respectively. So in other words, the proposed model and algorithm are able to identify the optimal new charging station locations in a way to maximize charging usage rate, and not only for the newly selected charging stations, but also for the existing charging stations that have been built. Here is the conclusion. The stage 1 model generates a satisfactory charging demand prediction result, which is explicitly measured by as the charging usage rate per week. And the stage 2 model is demonstrated to maximize the total charging usage of both existing and new selected charging stations, which improve the charging usage rate by 14% from initial random selection. I'm stopping here. Thank you so much for listening. Do you have any questions?
Thank you so much for presenting. In the interest of time and trying to keep us back on schedule, we're going to move the questions to the end of the session in case we do have time. So I'd like to allow Zaima to present their screen and get us rolling. Zaima Tasneem is a research assistant working under the supervision of Professor Yili Tong and is a Master of Applied Science student of Environmental Systems Engineering at the University of Virginia. She's currently working on ridership and the economic analysis of on-demand transit services.
Hello, sorry, I can't share my screen.
Veronica, can you make Zaima co-host? Thank you.
No, you can.
Thank you.
Great.
Hello, thank you so much, and good morning, everyone. I'm going to present my study on the impacts of on-demand transit service in terms of ridership and economy. I hope you all can see my screen. Is that good?
Yeah.
Okay. So at first, we all know how Uber works. We all know how Uber operates, and we're all very familiar with using Uber. So on-demand transit service is a similar concept, but in this case, it's being employed not in private cars, but in transit buses, where you can actually book a ride in a bus and they would take you from your origin stop to a destination stop using fixed or dynamic routing. And in doing so, it will improve the operational efficiency, reduce cost, and eventually reduce the overall congestion in a city. Now, for our case, for our study, we used City of Regina as our case study area, where they have actually implemented the on-demand transit service as a pilot program from August 2020, and it ran for 2 years as a nighttime bus service on a single bus route that was traveling from Norman View to RCMP. So here is a map which shows the transit stops. These are the green dots that, as you can see, which indicates the transit stops that were located in the city of Regina in each of the neighborhoods. And these were the ones which were implementing the on-demand service. So for our study, we actually used 4 data sets. The first one is a transit stop level ridership data. Then we have the amenities characteristics data, the on-demand transit data set, which gave a complete record of each ride that has occurred using on-demand service. And then we have the demographic data for each neighborhood that was actually implementing the on-demand service. So from the transit ridership data set, we actually get an overall view of the total ridership trend for each of the years. And as you can see from the graph, in 2018 and 19, we have a very high amount of ridership occurring in these 2 years. But from February 2020 onwards, we see a drastic fall in ridership. Now, this is the period where COVID hit the world. And as a result, we see a very low ridership occurring from April 2020 onwards. So for our study period, we chose May to August for the years 2020 till 2022 as our study period for our analysis. Now, we first look into the ridership effects due to the on-demand service. And to do that, we used a difference in difference model, which is actually used to estimate the causal impact of any specific intervention, which in our case is the on-demand service. And in doing so, we are going to measure the ridership effects due to the on-demand service for each particular region or area, or in our case, for each neighborhood. But before we can do that, we need to identify whether this model is actually suitable for our study or not. And for that, we need to do a parallel trend assumption test. So in this test, we basically see whether the pre-intervention and the post-intervention period follows a parallel trend or not. By that, I mean that pre-intervention means that before the on-demand service was implemented, and post-intervention means after it was implemented. And we have 2 groups, a control group and a treatment group. In the control group, it means all the transit stops that did not implement the on-demand service. And the treatment group means the transit stops that actually implemented the on-demand service. So before the ODT service was actually employed, the control and the treatment group are supposed to follow a particular trend. It is supposed to follow a particular parallel line. But after the ODT service is implemented, if we remove the data for their ODT ridership, then also we are supposed to see the similar trend in the 2 groups as well. So that's what we verify using this parallel trend assumption test. And here is the result that we got for the whole network. And as you can see, for both the control and treatment groups, we see a more or less parallel graph for both the cases, which means that this model is suitable for our study. So here is the DID model equation. Or in this equation, the dependent variable is the total ridership, or the total number of rides occurring for each stop. And treat is a variable, it's a binary variable, which indicates whether a certain stop is a control group or it's from a treatment group. Post is also a binary variable, which means if it's 0, then it means that it was before the ODT service was implemented, and it will be 1 if when it indicates that it's after the ODT service was implemented. And treat post is a variable, which is basically a product of these 2. And it will be 1 to indicate the post-treatment period of the treatment group. X is all the control variables that are going to be used, which in our case are the amenities characteristics for each of the neighborhoods. And from here, beta 3 is our coefficient of interest, which is actually going to give us the estimate of the average effects of ODT service on the ridership. So here is the whole analysis result for each of the neighborhoods in Regina that was implementing the ODT service. And this is the result that we are looking for. And as you can see, for most of the neighborhoods, almost all of the neighborhoods, they give a positive coefficient, meaning that the ridership has actually improved due to implementing this on-demand service, except for two regions, which is Rosemont and Regent Park, where we see a negative coefficient. So from here, we can say that for the overall transit network, we see a ridership increase. And this is also true for majority of the neighborhoods, which has actually boosted the ridership accessibility. But for Rosemont and Regent Park, we see a ridership is actually going down as a result of implementing this service. Now, once we have looked into the trend in ridership, now we are going to look into the economic impacts of on-demand service on different neighborhoods. And this is because, as we have just seen, that the ridership is increasing because of ODT. This means that inter-regional travel or travel between different areas have also been increased. And we have also seen that the travel time between two neighborhoods have actually gone down. So this is actually going to influence the economic growth of a certain area as well. So to examine that, we are going to look into these factors, this interregional travel increase and the travel time being reduced in terms of accessibility and connectivity due to ODT service, and examine their impacts on their economic growth. And along with these two factors, we are also going to look into other attributes of any neighboring areas that has, such as population, income, age, that also has a certain influence on the economic growth as well. So to do that, we are going to employ spatial econometric models, and we have three spatial models, that is spatial Durbin model, spatial lag, spatial error model. And here are the equations for each of these models. And in here, as you can see, Y is the dependent variable, which indicates the tax revenue for each neighborhood. X are the independent variables, which in our case, we're going to use population, age, employment rate, and accessibility and connectivity due to ODT service as our transportation variables. W is a spatial weights matrix, and rho and theta, these two coefficients are going to indicate the effects of a neighboring area that will have an influence on a particular area's economic growth. Now, before we can implement these models, we have to calculate the connectivity and accessibility due to the ODT service. So to do that, we used these two equations. So connectivity is basically a measure of the number of daily direct services or direct rides that are occurring using ODT service from one neighborhood to another. And accessibility measures the shortest travel time from one neighborhood center to another neighborhood center using the ODT service. So here is a spatial distribution map for accessibility in the years 2020 and 2022. And from the maps, we can see that for most of the regions, the travel time has actually gone down between neighborhoods, which indicates an increase in accessibility. Now, a similar graph is also seen for connectivity as well for the 2 years, where we see that the travels have increased for each of the neighborhoods over the years, which means it has also has seen an increased connectivity due to this ODT intervention. Now, once we have these accessibility and connectivity data, we now can employ the spatial models. But before we can do that, we need to find out which model is actually suitable for our analysis. And for that, we did 2 validation tests, that is a Lagrange multiplier test and a Wald test. And in both cases, we see that spatial Durbin shows significance in both the tests, which means that spatial Durbin is actually suitable for our study. So here is the result that we got from the spatial Durbin model. And as you can see from the table, If the inaccessibility increases over the years, we see the negative coefficient is also increasing, which actually indicates an improvement in economic growth of a particular area. As for the spatial lag terms, here also we see an increase in the coefficient, which means that for a particular area, if their neighboring areas' accessibility increase, that will also have a positive effect on that area's economic growth as well. And the similar situation is seen for connectivity as well, where we see that an improvement in connectivity is actually going to boost that area's economic growth as well. As for other attributes, that is population, employment, and age, now we see that if a particular area's employment, population, and age improves, we see a rise in economy or a larger profit in that area as well. But for its neighboring areas, if the neighboring area has a higher population, employment, or a higher number of younger population, then we see that the coefficient is actually going down. That means it has an adverse effect on that particular area due to that improved situation in their neighboring areas. So from this analysis, again, we can conclude that an improvement in accessibility and connectivity that is offered by the oddity service has actually improved the economic growth of a particular area, of a particular neighborhood. And this improvement is boosted over the years from year 2020 to 2022. As for the neighboring regions effect, if the neighboring areas have an improved accessibility and connectivity, that also has an additive effect on the area's economic growth as well. And this actually shows that if we improve the local transportation conditions for each neighborhood, that is going to pose a larger profit for a particular neighborhood or a particular city. Now, apart from these accessibility and connectivity factors, we have also looked into other demographics such as population density, employment rate, and younger population number as well. And we have seen that it also promotes the growth of economy in a particular region. And in addition, it also increases the chances of more on-demand services being availed in a certain neighborhood, which in turn boosts the profitability of the transit agencies as well. However, if the neighboring areas have an increased population or employment, then that is seen to have an adverse effect on that particular neighborhood. So finally, we have actually seen how the ridership and economic growth of a particular city is actually influenced by using this ODT service. And from our findings, we can actually say that ODT service did have a stimulating effect on the overall transit ridership as well as the economic growth because of the improvement in accessibility and connectivity in on-demand service. And from our study, we did see that accessibility and connectivity has improved over the years. And this improvement has not only stayed limited for that particular region, but it also had an influence on neighboring areas as well. So finally, I would like to thank NSERC and President Seed Fund, CTR Vagina, for providing us with the data resources, and also my professor, Dr. Tang, for her continued support. And with that, I conclude my presentation. Thank you all for your patience.
Thank you all. And thank you all for being patient with the Zoom issues we've had this morning. So I did type into the chat box that we'd like to answer all Q&A there as we move forward and try to adjust back to our time. So the next presenter is Lynn Su at the University of Texas at Austin. She's actually going to present, I think, in another Zoom room. So I'll play her recording. Lynn received her BE in Civil Engineering from the Shandong University of Science and Technology in June 2020 and her MS from the University of Florida in May 2022. She joined Dr. Cochman's research group in August of 2022, and her research areas in SAEVs, and is currently working on the co-location of public and private charging stations for Cruise's new SAEVs in the Austin area. Her research interests also include shared micromobilities, transportation equity, and the applications of machine learning. Let me pull open her slides. Let's see. And can someone confirm, Priyanka, that you're able to see this recording?
Yes.
Okay.
Everyone, thanks for joining this presentation. I'm Lin Su, a first-year PhD student working with Dr. Carl Kaufman at UT Austin. What I'm going to talk about is citing the public-private EV charging stations across the Austin area. The electrification of transportation is an important part of society's efforts to reduce greenhouse gas emissions and improve air quality. Recent years have witnessed rising purchases and use of electric vehicles around the world. There are now more than 3 million EVs on the road and over 130,000 public chargers across the United States. By 2030, with an estimated 28 million EVs on U.S. roads, approximately 2 million level 2 chargers and 172,000 level 3 chargers will be needed in public locations in addition to home EV chargers. Sufficient charging infrastructure play an important role in the development of EVs. Many researchers suggested that funding EV charging infrastructure can be private and public. Given EV charging infrastructure shares some good characteristics similar to public infrastructure. In addition, private EV fleets may do well to share sites with public chargers. Co-locating private charging stations with or alongside public charging stations could maximize utilization, share installation and operation costs, and offer convenience for EV drivers. In this study, the city of Austin is used as study area. Our objective is to explore current EV charging station distribution, simulate charging demand across Austin, and analyze a potential site for future public-private EV charging stations. This table summarizes the number of charging stations and charging ports in Austin area based on the data from the U.S. Department of Energy. Public charging stations in Austin are level 2 and DC fast charging stations, with more level 2 stations in service. If all charging cores in Austin are occupied, a total of 979 EVs can be charged simultaneously at level 2, 125 of which are at the Tesla destination chargers. Generally, charging stations operated by Tesla often provide more charging ports with higher power compared to other EV charging networks and can charge more EVs at once. Given the number of households in Austin provided by the U.S. Bureau at 2020, each level 2 charging port serves roughly 17 EVs and 403 households. Level 2 charging stations in workplaces account for 37% of all charging stations, ranking top among all location types, with parking lots attached to commercial areas and airports falling behind, accounting for 24%. DC fast charging stations are not as common as level 2. There are 37 DC fast charging stations with 123 charging ports in Austin. Tesla superchargers make up 76% of total charging ports. Many public DC fast charging stations are scattered along the I-35 freeway or within downtown Austin, located in parking lots near restaurants and shopping malls. 17% non-Tesla DC fast charging stations are co-located with level 2 charging stations. Each pedestal only accommodates one charging port. As for simulating the charging demand across Austin, The agent-based model Polaris is used to fully simulate travel demand, network, and operations. It relies on travel demand model and supply models to synthesize and simulate agent travel and EV trips across large regions. Regarding the demand side, Polaris synthesizes a representative population of the given region with socioeconomic information provided by United Census Bureau. Within this simulation environment, travel demand models are used to simulate agents' behavior and actions across the region on a single day. Polaris integrates an energy consumption model during runtime to simulate EVs appropriately, curing link-level consumption based on a machine learning model. When the state of charging of the EV is identified to be below a specific threshold, it triggers the estimation of the energy demand, considering nearby available charging resources, thus simulating the charging behavior. The output demand file contains comprehensive information about charging behavior, such as charging locations, charging time, charging level, and duration of EV charging. Taking the charging demand derived from the charging behavior simulation, the right figure visualizes the EV charging demand within the city of Austin. Three neighborhoods demonstrate a notable concentration of charging demand. That's Zehra downtown and Central Austin, the intersection of Highway I-35 and US 290, and the domain area. In addition, parking lots attached to Austin International Airport also present a relatively high charging demand. Among private EV users, 88% had 88% prefer to charge their EVs at home, and the remaining 12% will get their EV charged at public charging stations. Home charging is mainly relying on level 2 chargers. As for EVs head to public EV charging station for charging, 87.5% charged by level 2, while 12.5% use DC fast charging station. The majority of charging activities occur between 3 p.m. and 6 p.m., accounting for 30% of total charging trips as shown in the below figure. The peak demand happens significantly between 5 p.m. and 6 p.m. time slot. On average, the waiting time at charging station is approximately 41 minutes, with 82% of the waiting trips occurring at level 2 charging stations. Based on the distribution of charging station and possible charging demand, the two sites are manually selected as a potential site for deploying future public-private EV charging stations. Since UT campus has heavy daily traffic from students, faculty, staff, or visitors, which contribute to high charging demand, but the whole campus is a charging station desert with just 2 level 2 charging cords available near the campus west side. San Jacinto Garage and Brazos Garage are great transportation hub within a 10 minutes walking to almost every building on the UT campus, making it easy for travelers to charge their EVs and walk to their destinations. Thus, the 2 garages are selected as first potential sites. However, considering the land management of UT campus, the process of applying for land permits may be complicated. So the garage within the residential neighborhoods on the north side of the campus and the commercial area to the campus south side, where many hotels and restaurants are located, are also ideal locations. The second potential site is HEB parking lots. It's also nearby an intersection of Freeway I-35. The example of designs are shown at right. Commercial areas such as HEB always witness high traffic volume and will also generate high demand for EV charging. In addition, since parking lots is along the I-35 freeway and near a freeway intersection, it could provide easy access for long-distance EV trips. Studies have consistently recommended locating charging stations along major highways where charging demand is typically heavy, thus achieving profit maximization. There's already a level 2 charging station located here, so it's a good site to co-locate a new EV charging station to try public-private collaboration. The planning problem faced by many charging station investors is how to provide charging service to customers at a lower economic cost of charging facilities and practical operations. Cost of owning and operating EV supply equipment mainly includes equipment costs, installation fee, operation and maintenance expenses, and additional capital cost. The Rocky Mountain Institute paper reported the range of level 2 and DC fast charger costs in the first table. For both level 2 and DC fast chargers, equipment cost varies greatly with power rating. Generally, level 2 home chargers are less expensive than non-residential chargers since they are well-mounted in weather-proof locations like garage. Commercial level 2 chargers and DC fast chargers for public access are usually installed on a pedestal and exposed to the elements, leading to additional costs to the chargers. According to the Future Energy, a public dual-port level 2 EV supply equipment unit costs around $5,500 and can charge 2 vehicles at once. Besides the cost estimation presented in the above table for single-port DC fast chargers, the equipment cost for dual-port 50 kilowatt DC fast charging station ranges from $25,000 to $35,000 per charger. Besides the equipment cost, the ICCT working paper also provided the installation cost for EV charging station by charging types and number of chargers as shown in the table. Unlike equipment costs, which are relatively static and depend on the level of charger, the installation cost fluctuates over time and can be subject to market conditions. Local labor rates significantly impact DC fast charging installation cost, which is increasing as much as $350 per dollar increase in the labor rate. The cost of installation also varies greatly by location, with an estimated range of $600 to $12,700 for level 2, and $4,000 to $51,000 for DC fast charging. Generally, more EV supply equipment units installed at once usually lowers the average cost per unit, especially at commercial sites. In conclusion, the city of Austin serves as a case study, highlighting the need for both public and private support to develop EV supply equipment. Co-locating private EV charging stations with or alongside public EV charging stations provides more cost-effective way to maximize charging plugs utilization and offer convenience for EV drivers. Areas with high demand but limited access to charging stations, particularly existing parking lots at commercial areas or transport hubs, gas stations, intersections, and nearby highways, are identified as potential sites for a new EV charging station in this study. As you all know, Cruise has launched Austin Beta Rider community with driverless rides in Central plus downtown Austin at night from 9 p.m. to 5 a.m. As the EV fleet grows, more EV charging stations are needed. To promote EV adoption, the U.S. government plans to build a national network of 500,000 EV chargers by 2030. A 5 billion national electric vehicle infrastructure program was launched in 2022 by U.S. Department of Transportation to build a network of stations along major highways in the U.S. This is the end of my presentation. Thanks for listening, and feel free to contact me if you have any questions. Thank you.
All right, thank you, Lynn. The next presenter is actually myself, so I'm going to queue up my screen. And please continue to type in questions in the chat box if you have any. All right, my work is on Americans' opinions and interests in EV smart charging programs. I recently graduated from the University of Texas at Austin with my PhD, and I've since joined UC Irvine as an assistant professor in the School of Engineering in the Civil and Environmental Engineering Department. Let's do the screen here. One moment. Let's see. I think I have to do a new share. All right. Can you see my next slide, Priyanka?
No, it's just the first one.
Okay. Let me start this over again. All right, now we have it.
Yeah.
All right, so I'm going to go over some terminology here because I know this is a transportation conference and I don't want to assume everyone has the same understanding of smart charging. So what do I mean by smart charging? Well, first, I mean unidirectional V1G charging that is done by the user, typically due to incentives from the local power company. The most common scenario is where that power company creates an EV-specific or whole house time of use electricity rate, where the vehicle owner can charge their EV during the grid's off-peak hours at lower cost. And this is usually done with an app or timer. For example, there's an app called Flex Charging where you put in your type of EV you drive, so it knows the max battery capacity and charging speed, whether you have level 1 or level 2 home charging, whether you have rooftop solar, and what residential electricity rate you pay, so that you're able to either lower your electricity costs, decrease charging emissions, or do both simultaneously. The other alternative to smart charging is with supplier managed charging, or SMC. It's not widely offered since EV adoption has until recently been pretty small, and grid operators, at least in the United States, were not previously required to accept aggregated demand response programs with EVs. So in the future, with some rule changes, we're likely to see more SMC programs, especially in areas with a high concentration of EVs or need for flexibility in charging demand. And I know that others will sometimes lump bidirectional charging or vehicle-to-grid V2G into smart charging, but I'm not doing that in this study, although certainly there are applications to discharge power back to other loads, buildings, homes, and the grid at large. So again, why should we be focused on smart charging? As we've seen in Texas, where I was from, and other regions around the world, when it gets really hot or cold, the demand for electricity increases, and it may also impact the performance of renewables, which are increasing in its capacity on the grid. At the same time, our infrastructure is outdated, not well maintained, and certainly not sufficient for a large growth in renewables. So the whole premise of this is, instead of building a watt of energy, what if you removed a watt of demand? And this goes into demand side flexibility. And certainly in solar rich regions like California, where I'm currently located, in Australia, the net load curve, which is demand minus renewable generation, is looking more and more like a duck. And this requires a lot of fast response generation in the evening to meet the peak demand when solar generation goes down. If we were to let people just charge their vehicles when they arrive home, That would increase that net load curve in the evening, aggravating peak demand, requiring more generational capacity and certainly emissions as well. And so if we lump V1G and bidirectional charging together, there are expected benefits of lowering customer power bills, increasing grid reliability, avoiding brownouts, and reducing curtailed renewables. A lot of the focus in the research community is on V2G, but V1G is far simpler and can be done with through apps today, and really is one of the most critical hurdles that we need to get across before we can even look at V2G. So what have we found in the literature? Well, there were two really early real-world interventions or pilots that demonstrated EV smart charging. One was in Canada, where they interviewed 30 drivers participating in the supplier-managed charging program and found nearly 3/4 would accept a future program when given the option to set both a minimum battery level and a departure time. For example, like I want to have my vehicle fully charged up by 7 a.m. in the morning each morning. And over half of the participants would also accept a future program if paid less than or equal to $10 a month. So participation incentives may be small. Some interventions have also been tested outside the home. So there were 2 public parking garages in Malmö, Sweden, where there were interruptions due to charging. Drivers that had a plug-in hybrid EV, so that's typically 40 miles of EV range, and then you rely on your gas engine, felt this increased their gas costs because the battery side was not fully charged when they left the garage, whereas those who had a fully battery electric vehicle had to spend additional time finding alternative public chargers. A subsequent web-based survey of Stockholm area residents with a plug-in EV found that 40% would likely accept a supplier-managed charging, regardless of how long the charging was interrupted or controlled, because of the perceived environmental or grid stability benefits. And a study out of Australia found that BEV owners actually preferred supplier-managed charging over doing it themselves with an app or timer. And so maybe this experience of charging can influence future expectations or future charging behaviors. What's the response to some participation incentives? We found that engagement with smart charging was conditional on reducing charging costs. Others have found that maybe half of people would place an emphasis on charging costs, but others would have other charging attributes that they want to focus on. EV drivers' willingness to participate in a smart charging program was considerably high in some studies. For a program with a penalty for gaining control of your charging, but no additional incentive, so like no free charging equipment, no financial incentive, no kind of insurance policy if your vehicle wasn't fully charged, about 28% of EV drivers would still participate in this program. And this suggests a really low-hanging fruit for an opt-out smart charging program that auto-enrolls EV drivers. For that same type of no-frill EV smart charging program, but with an incentive of $500 per year, the participation rate would climb to 64%. Of those in the Canadian real-world demonstration project, about 2/3 said they would participate. So similar overall percentage findings, but there they said that they would receive a credit of $15 or less per month. So that's a lot less than what we're finding in this other study. Acceptance of supplier-managed charging increases from 35% to 56% among current ICE drivers if a charging app has an override feature for supplier-managed charging. So that's another incentive that people can use in designing these programs. And one study found that nearly 28% of respondents preferred supplier-managed charging to unmanaged or a form of guaranteed charge by the morning, as long as it reduced charging peaks and aligned with solar power and didn't substantially increase charging durations. The implication here is, again, that user-centric supplier-managed charging programs are what gets to that floor level in participation, and then any additional monetary benefits that the user can get will lead to a larger jump in participation. But researchers show that there's diminishing rates of returns in that participation percent agreement. So what are we doing right here? All of the prior papers looked at typically non-US countries but one, and we know that public's trust in new technology it depends upon that region, and particularly, for example, the power suppliers and their trust in their local power companies. So that's why we're focusing now on Americans' perceptions of smart charging programs. In this work, we gave respondents 7 charging alternatives to select from instead of a dichotomous choice like you do manage your charging with an app or you don't. You allow your company to have control or you don't. And although we recognize the value of discrete choice methods where you vary those key attributes with narrow set of choices, we were just focused on a simpler choice experiment that we could roll out immediately in November, December of last year. We also segment the minimum monetary incentives for supplier managed charging participation by their preferred charging style without any incentive. And this allows us to show the heterogeneity in responses by preference and give information on the averages for each group. And we measure the willingness to pay monthly fees to opt out of a supplier managed charging program and use different prompts to test the effective language on changing those fees. So again, we deploy this to an online paneling company called Dynata between November and December of last year. So this is all on the tail end of when gas prices were really high. So that could have an effect of people choosing to smart charge their vehicle to lower charging costs, although we certainly don't know that. We had over 1,000 responses that were retained after cleaning, and we did population weight our results based on gender, age group, highest education received, and the US Census region. Some of the main survey questions that we asked respondents included their perceptions of EVs, smart charging benefits, supplier managed charging, and user managed charging, and the power grid. Respondents listed their knowledge of supplier managed charging and the preferred PEV charging style, expected compensation with supplier managed charging, opinions on various EVs and renewable topics, the minimum willingness to pay a monthly fee to leave an auto-enrolled SMC program. And there was also the optional section to answer questions about the willingness to pay for bidirectional features and expected use. And then again, the likelihood to participate in V2G programs given various conditions. But I'm not going to present the results from that study in this presentation. Again, we asked respondents to select their preferred charging style, assuming that they had a 250-mile range BEV, a level 2 home charger that provides between 10 and 20 miles of range for every hour plugged in. And we just said, what would you typically choose would you let your local power company direct control charging, given your expected weekly driving and then expected charging habits? So there were 3 choices that answered yes in the positive. Yes, I would like to wake up with a full charge, but don't do anything during the day. So nighttime only. Yes, I want to optimize grid demand throughout my community so you could do it whenever. Yes, but only when needed, like to break grid strain on days of high energy demand. The 4th one was kind of maybe, but I need more information to feel confident in giving up total control. So in the future, they may be willing to adopt supplier managed charging. No is the first negative. That's the ones who say, no, I don't want to cede control for any number of reasons, but I'd be willing to use an app or timer. The last negative was no, I just want to plug in my vehicle, don't think about it, just start charging and then stop once it's full. And another was, I'm really unsure even with all these choices that we gave them. So let's dig into some summary statistics. After population weighting all of this, we find that there are differences between people who own an EV, have that gas engine vehicle, or currently don't have any vehicles. Those with an EV shown in light blue preferred supplier managed charging options on the top. Those with no vehicles are more unsure and or would prefer unmanaged charging or dumb charging here. And about a quarter of gas vehicle owners are on the fence with supplier managed charging. They just need more information to feel comfortable giving up that control. Now, what about that model for preferred charging style? We first did a multinomial logit model and then looked at nested logits where we grouped together supplier managed charging options. We confirmed with a log likelihood ratio test that specification was not statistically different from the multinomial logit model. And so we ended up just using the multinomial model. We did play around with using ordering, but we were unsure just exactly how to do the difference between nighttime versus grid strain days when we're ordering control per se. We did remove the unsure other responses from our final estimation, leading to a sample size of 922 respondents. and we use unmanaged as the base. And so with our model specification, we find that the negative ASEs imply a preference for dumb charging. So who could potentially overcome that negative preference for dumb charging? If you have a household with a BEV who pays wholesale electricity prices, they can sort of like overcome it for nighttime supplier managed charging and daily grid optimization for the local conditions in their community. Similarly, like a part-time worker who pays time of use prices for their house and is in a 4+ vehicle household where one of them is at least a BEV, can overcome the negative alternative specific constant for user managed charging with an app or timer. So I'm not going to go over all of our covariates here. There are a lot that we threw into the model. We did keep some predictors that were statistically insignificant, but we do have the rationale that they may be relevant for future studies, or they are typically behaviorally significant for similar technological adoption studies. So looking more into the coefficient directions, the coefficients for this model are positive for male for supplier managed charging at night and daily optimization for the local grid. The other three options were not statistically significant at the 95% confidence level. Adults that are between ages of 35 and 64, relative to young and old adults, are less likely to prefer SMC at night relative to the other choices. Educated adults who are more likely to choose SMC for daily grid optimization or be on the fence for SMC. As the households have more vehicles, adults prefer charging options relative to dumb charging. Those who own a BEV prefer these charging options more than the others, perhaps because they have experience with charging and find these options would be easy and convenient. Smart thermostats line up with, grid strain days, so perhaps those smart thermostats already participate in demand response programs like what we had in Austin Energy. Wholesale power prices line up with supplier managed charging, daily grid optimization, and grid strain days. And people with time of use prices or energy price differences are known in advance can schedule charging to low cost off-peak hours with an app or timer. So that's why we see a positive coefficient for that variable. Here we observed respondents' values on statements related to like EV transition and smart charging benefits. And so people who agree that they would want to plug in their EV and not think about it are fine with SMC at night only, so long as the vehicle is fully charged. Those that believe supplier managed charging has more risks than benefits prefer dumb charging. Those valuing smart charging benefits for the grid and renewables prefer all charging styles relative to dumb charging. And if we were able to kind of wave a magic wand, show practical significance here, BEV ownership and wholesale energy prices were the most likely to have that change in the preferred charging style. So if everybody shifted from not owning a BEV to having a BEV in blue, we're likely to see more people choosing user managed charging with an app or timer, or doing it for night only or for the day. People who now are likely to pay wholesale energy prices are very less likely to do unmanaged charging and more likely to do daily optimization and grid strain only days. Shifting ahead into that dollar incentive, we had the similar setup of that, assuming they have a 250-mile range BEV, they have level 2 charging at home. We said, we would do overnight charging with the supply managed charging scheme. Daytime, we'd only interrupt it during those 5 days of the year where there's grid strain. So it's a combination of SMC at night and SMC for grid strain now. And we tell them they have to stay enrolled for at least a year to receive this one-time bill credit. And again, we kind of designed it to be user-centric. Like, we're going to study your charging schedule and create a program that does it for you without really interrupting your needs. So let's move right into our model. This is showing the breakdown by preferred charging style. And so one-time credits were lower for individuals preferring supplier managed charging outright. This is, $100, $96, $100 compared to those who wanted user managed charging. That was $126 on average. Those who are on the fence with supplier managed charging only need an additional $9 to $13 to get them there. This next column on the right is this yearly or annual credit. So this is an addition to being enrolled in a program for at least 1 year. it shows that there percent of people who need more than $20 increases by like 57% for user managed charging, because the slider was only between $0 and $20 now. For that one-time credit, it was between $0 and $200. So it is interesting to see that more people need a higher benefit. Kind of rushing now to be able to finish on time. We estimated these models on financial incentives using a total bit model, where we're able to capture all those Ys between our slider scale between 0 and 200 and 0 and 20. Those who selected more than $200 or $20 are censored out. For that minimum one-time credit, where this table presents results and finds that females that do not identify as Asian or Pacific Islander or Asian American are between the ages of 18 and 24 years old and do not trust their power company to always guarantee a fully charged EV. They perceive smart charging benefits of increased grid reliability as important, are estimated to have higher minimum one-time payments to allow their local power company to modify EV charging. While those who are Asian American males who agree that EV owners should pay higher fees on power bills and are interested in long-range BEVs exclusively, place a lower value on those one-time bill payments to permit supplier-managed charging. If I skip now to the annual credit, we find that those who do not identify as white or Hispanic Latino agree that smart charging is a net good for society and perceive smart charging's benefit of increasing grid reliability, are estimated to have higher minimum annual payments to allow supplier-managed charging, while those who are young adults who are between the ages of 18 to 24 have a maximum household pre-tax income of $30,000 and agree the power grid can support the government's EV adoption goals, place a lower value on annual bill payments to permit supplier-managed charging. Our last kind of study looked at if we auto-enrolled people into supplier-managed charging, what would they be willing to pay to leave that? And so we asked them the following text, where we had this control group that was given the red text, which is more altruistic. So it's power company does this program to prevent EVs from charging when demand is high. It reduces the cost that all customers pay. What's the highest fee you'd pay to charge whenever you want? The pro-freedom group did not receive that red text. They were only asked, how much do you value the freedom to charge as you want? And so we randomly assigned respondents into one of two groups, and we double-checked that the demographics were truly random when it was assigned. So we can just look at now the average willingness to pay to leave this program between the control group and that pro-freedom group. And we're finding that there was statistically significant differences between these two averages. And we found that those who would pay less than the pro-freedom group treatment text do so not because they don't want or value the freedom to fully charge, but because they may not want to or believe they should pay extra for that flexibility. And so they believe they ought to have the freedom to consume electricity when they want. And there was a significant change in willingness to pay. This fee for those that are Americans ages 18 to 24, 35 to 64, have at most a high school education and who are not Black and who have received the treatment text. So jumping right into the policy suggestions, time of use prices trigger participation. Those paying temporally varying prices prefer supplier-managed charging and user-managed charging options to dumb charging. Those that had a BEV were likely to select supplier-managed charging and user-managed charging for some options. Respondents who said it's easier to install a home charger were more likely to smart charge. We also found that attitudes were great predictors compared to models that didn't have these attitudinal statements. And that about 40% were willing to accept some form of supplier-managed charging, and about a quarter simply needed more information to get there. And this was asking it before they had any financial incentive to answer that question. Compensate wisely, because we find that people who need a switch from user-managed charging to supplier-managed charging need an additional $30 per vehicle more. But we know that Americans on average were willing to accept $126 to sign up and then $17 per year of ongoing participation. We find that altruistic messages were effective, and this leads to an increase in willingness to pay to leave an auto-enroll program. So this could be geared to designing fees for people who are not willing to change their dumb charging patterns at all. And there also is a need to have these kind of altruistic messages for those on the fence that may help stagger them or shift them to accepting supplier managed charging. This V1G paper and a new V2G study is available on Dr. Hochman's website. And I want to thank you for listening, and thank you for our sponsors. If you have any questions, please feel free to jump and put them in the chat. I want to move to our next speaker, Tanjeeb Ahmed. If you want to queue up your presentation while I announce you.
Thank you, Dr. Dean.
And I don't know if I have your bio. Would you like to introduce yourself?
Yes, of course. So I'm a PhD candidate in the Transportation Science program of ITS at the University of California, Irvine. And I completed my master's in both Transportation Science and Urban Planning. And my current research is oriented towards modeling and analyzing complex activity travel behavior in the context of traditional and emerging transportation modes. So I'm particularly interested in the implications of multimodal and shared or autonomous mobility systems in improving mobility, reducing VMT, and promoting equitable access. Thank you. Should I start my presentation now?
Yes, please.
You can see my slides, right?
Yes, if you want to go into full view.
Okay, thank you. Okay, so hello everyone again, good morning. So a study comprises an estimating a latent class analysis or LCA model to, to categorize trip chains using household travel survey data from 4 MPOs in the United States. I'll first go through the major findings and then discuss the details of the study. So from the classification model that is estimated using the latent class analysis, we obtained 4 distinct classes or groups of trip chains. And from these classes, we find one of them, most of them having a prevalence of car-based trip chains with 1 or 2 stops ending at home locations, mainly for maintenance activities. And we find one class which has the highest representation of complex trip chains and multimodal travel characteristics. And finally, there is a substantial representation of non-motorized transport or NMT, transit and multimodal trip chains in classes 2 to 4, which is 3 of the 4 classes that we identified. And from the class membership prediction model estimated using the multinomial logic regression framework, we find that higher income and multi-member households prefer simple car-based trip chains for errands. And women are more likely to use car in both simple and complex trip chains, and pedestrian-oriented link density positively affects the propensity of NMT and transit-based trip chains. And finally, the multimodality in trip chains, we find that it is positively associated with the transit frequency at the home locations. So a trip chain is a series of trips with intervening activities. In a trip chain, there is one primary activity and at least one secondary activity. For example, the diagram on the right shows no trip chain between home and work, but there is one trip chain between work and home with 3 secondary activities. As noted by several studies, the frequency of trip chain formation has increased throughout the world. And while the increased frequency is the result of travelers combining trips and activities together due to time and cost constraints, there is the city's land use distribution and traffic conditions play an important role in the formation of these trip chains. So in a nationwide study using the 2001 NHTS dataset, McGuckin found that over 27% of the workers form trip chains in their commute. And this percentage increases to 60% in the 2017 NHTS dataset based on findings by Ahmed and Highland. And to support the travel demand management policies, an in-depth understanding of the specific trip chain patterns or types is important, as it directly impacts mode choice distribution, VMT, and congestion. So motivated by this opportunity to support the policies, this study aims to investigate the types of trip chain patterns that travelers make and the socio-demographic, land use, and transportation system characteristics that influences such patterns. Specifically, the objectives are to explore the existence of distinct trip chain classes, identify distinct classes of trip chains, and analyze travel and activity patterns alongside the socio-demographic characteristics of the distinct classes. There are two definitions that are crucial for this study. The first one is the definition of trip chain. And as there are no established definition of trip chain, we propose one combining both activity type and duration to encompass the advantages of this criteria, which are used separately in other studies. So we define trip chains as having a series of trips having one primary activity and one or more secondary activities. And we define the primary activities as home and home work and any other activity with a duration greater than 4 hours. And all the secondary activities in a trip chain are non-home or work and activities which are less than 4 hours. In each trip chain, there could be several secondary activities of different types. We group them into three categories: subsistence, maintenance, and discretionary. We select the dominant secondary activity in a trip chain as the one with the longest activity duration in that trip chain. So in this study, I used the 2018 and 19 household travel survey data collected from 4 MPOs in the US. And these are CMAP, or the Chicago Metropolitan Agency for Planning, PSRC, or Puget Sound Regional Council, SACOG, or Sacramento Area Council of Governments, and WCOG, or the WhatCom Council of Governments. So these collected dataset contain trip-level activity travel data for weekdays and weekends. The table provides an overview of the area and sample observations from each of these MPOs. We see from here that the PSRC is the largest in terms of area, and CMAP is the largest in terms of the sample population. And except CMAP, all other MPOs have up to 7 days of data for each person. To prepare the data for analysis, we applied the trip chain definition I mentioned in the earlier slide and extracted only the chain trips for the analysis. So in total, there are 47,251 trip chains in the dataset. And we only restricted the mode options to NMT, auto, and transit, as there are insufficient observations for other modes. So after applying the definition of trip chain and filtering the dataset for unreasonable values, we obtained, as I mentioned before, for 47,251 trip chains. So looking at this pie chart, these trip chains represent 68.5% of the trips in the whole dataset. Sorry, skips going to the next slide. So I then subdivided this proportion of trips in chains under 4 MPOs. And we can see that the SACOG has the most representation in these trip chains. So our research method has 2 main steps. At first, we estimate a latent class analysis model, or LCA, to categorize the trip chains into distinct classes. The LCA model reveals the unobserved heterogeneity in observations through a set of given indicators, which I will describe in the next slides. And second, we estimate a multinomial logistic regression model to model the propensity of selecting a trip chain class with respect to the trip chain maker's socioeconomic and home location characteristics. So in this slide, we see that on the left, we see the table where we see the activity travel indicators that we use to classify the trip chains in the LCA model. The table on the right lists the socio-demographic characteristics, which are used as covariates to explain the assigned class memberships in a multinomial logic model framework in step 2. So after after checking the LCA models from 2 to 10 classes, the 4-class model is selected considering the goodness of fit statistics, the posterior probability matrix, and class interpretability. So each chart here shows the probability of response in a variable category given the class membership. So for example, we see that the class 1, they have very high propensity of having 1 to 2 stops, and they also have a high propensity of having more maintenance activities than other classes. Similarly, we see from the mode indicator that class 1 is has a high representation of auto, and class 2 is a high representation of NMT and transit. So we find some distinct patterns from these charts, and we identified there are 4 classes. Oh, my PowerPoint is not working properly today, sorry. So identified 4 classes. So class 1 is the simple trip chains with 1 to 2 stops for short duration maintenance activities. And class 2 is a simple NMT transit trip chain with 1 or 2 maintenance activity stops within 10 miles of home location. And we find class 3 as the most complex half to full day trip chain classes that also includes discretionary activities. And class 4 is a simple weekday trip chains with 1 to 2 stops for long duration discretionary activities. So this table shows the results from the class membership prediction model, where class 1, representing the simple auto-based trip chains, is considered as the reference alternative. So in conclusion, I would like to say that we identified 4 highly distinct trip chain clusters, indicating that there are clearly different types of trip chains that travelers make, and which are also strongly associated with the socioeconomic and home location characteristics. Therefore, depending on the category, trip chains can have a wide range of impacts on the transportation systems. So behavioral models, forecasts, and targeted transportation policies should distinguish between the different types of trip chains, such as those identified in the study, because the policies that might be effective for impacting one type of trip chain may be ineffective for the other trip chain types. Thank you all for listening, and I'll be happy to answer any questions.
Thank you all, and please continue to put your questions in the chat box or the Q&A box, and we'll have the presenters answer it. And at the end, we'll have a Q&A session for all of the speakers. I'd like to cue it up to our next presenter, Syeda Narmeen Zehra. She's a transportation researcher and MS student in civil and environmental engineering, specialized in transportation engineering at the University of Alberta. She is being supervised by Dr. Stephen Wong and is a member of the Resume group. Her interests lie in advancing transportation resilience and equity and facilitating disaster risk mitigation. Her current research focuses on behavioral analysis during wildfire evacuations and flooding events, aiming to enhance transportation strategies in disaster scenarios. She serves as the social media coordinator in the TRB Critical Infrastructure Protection Committee, AMR 10. Beyond her research pursuits, Narmeen actively engages with STEM-focused events and community organizations through volunteering. When not glued to a digital screen, she enjoys long walks and exploring new places. Narmeen's favorite mode of travel is public transportation and looks forward to skateboarding in the future. Great.
I'm just trying to share my screen. Give me a moment, sorry.
Sure, I had the same issue too, so don't worry.
It's so confusing. Okay, share.
We see your full screen, so.
Do you see my presenter view as well?
We do. The last option you had, we show the full screen. Yeah.
Okay. Let's get this, stop share. And then I go here. Share screen. Share. And Can someone confirm if they can see my presenter view?
We see the full screen, not presenter view.
Okay, perfect. All right. All right. Hi, everyone. Welcome to my presentation on review on wildfire evacuations, infrastructure, transportation modes, networks, and planning. My name is Syeda Narmeen Zehra, and I go by Narmeen. I'm an MSc student at the University of Alberta studying transportation engineering. I am part of the Resume group and currently research on the behavioral side of wildfire evacuations. Today, I'll be sharing with you some critical insights on the links between transportation sector and wildfire evacuations by focusing on 4 understudied areas. Before we dive into the presentation, I want to acknowledge the generous funding provided by Infrastructure Canada and the Resume Group for providing me with the platform to pursue this research. Here is the outline of the presentation, where we begin with going over the significance of wildfire evacuations, the methodology employed in this review, the current research on resilience of infrastructure, modality, transportation networks, and planning, an analysis of the 4 modules by identifying the interdependencies of various factors, and finally, I will conclude the presentation with future research directions. Some of the most devastating wildfires have taken place this past decade, leading to substantial evacuations. For example, in California, over 1 million people were ordered to evacuate between 2017 and 2019. In Australia, the 2020 January wildfires required the evacuation of tens of thousands of people from the seaside towns. This slide shows the average number of wildfires that have taken place in these countries each year. Canada has witnessed the evacuation of over 100,000 people in 2023 alone, and this year has been the most severe wildfire season on record. The wildfires so far prompted evacuations in multiple communities throughout the country, resulting in poor air quality within the region, in the US, and the smoke also drifted to parts of Europe, and unfortunately, fatalities of those fighting on the front lines to contain the spread. Globally, these wildfire evacuations point toward transportation and logistic challenges, which are heavily dependent on the existing state of infrastructure, the multiple forms of modality available, the transport network's performance, and evacuation planning that supports resource allocation, strategies, and policies. Some of the most vulnerable regions to wildfires are densely wooded areas and urban wildland interfaces, while the type of residents in these neighborhoods range from wealthy seasonal vacationers to low-income multi-generational households. Underserved groups like the elderly, disabled, and low-income residents require tailored evacuation solutions. Most of you would be aware of the following areas from an engineering perspective, such as identifying evacuation routes and having secondary routes in place for redundancy, having efficient traffic management strategies in place to curb congestion, having a communication system in place to issue real-time alert, and finally, interagency collaborations for cooperation among emergency services and transportation agencies. Despite the continued threat of wildfires, transportation systems and its associated infrastructure remain largely unprepared to cope with these evacuations. We set out to uncover key insights to describe and link these 4 under-researched areas and craft directions that can help devise and improve wildfire evacuation plans. This review addresses 4 research questions based on limitations of literature and practice. Number 1, how was transportation infrastructure impacted before, during, and after wildfire evacuations? Which modes of transport other than private vehicles can be or have been used during wildfire evacuations? What role do road networks play during wildfire evacuations? And finally, what transportation planning actions have been taken and what needs still exist? We conducted a systematic review of literature on Scopus, Tiller and Francis, TRID, and Google Scholar between the year 2000 and 2022. The final review contained 89 literature from systematic review and 113 from additional search. This included peer-reviewed articles, blog posts, books, conference proceedings, manuals and design guides, news articles, and reports. We begin the review on infrastructure where we found that wildfires have damaged surface transportation infrastructure, buried utilities, and vehicle sensors on highways. This has led to closures of exit routes during evacuations in the past. Interestingly, existing surface infrastructure such as roads, non-flammable land cover, recent burns, and ridge lines can act as barriers to reduce the likelihood of fire spread and provide safe places for firefighters. Wildfires can also lead to debris flow events and flooding that damage roads and infrastructure, especially in areas with high burn severity, steep slopes, and low vegetative cover due to hydrophobic nature of the soil. We did not find any explicit guidance for surface transportation design that considered wildfire evacuations and any resulting impact loads in its design and rehabilitation strategy. Wildfires often start due to electrical systems, so public safety power shutoff events are often implemented to mitigate the risk. However, these events can disrupt transportation activities, such as when traffic signals lose power and enforcement personnel are limited. We also note that communication disruptions can pose a great threat to transient populations and those with limited access to mobile phone services during evacuations. From a modality perspective, most evacuations are carried out using private vehicles powered by fossil fuels. But the rising market share of EVs introduces challenges in planning for a wildfire evacuation due to limited public charging infrastructure and comparatively longer charge times. Research has also shown that buses are crucial for evacuating low-income and underserved populations during disasters. We further noted that coastal towns and islands faced additional challenges in wildfire evacuations due to limited capacity. Boat and ship-based evacuations have been reported in parts of BC and Australia. Air evacuations, although quick, are super challenging for removing people from high-risk zones due to limited capacity and resources. They have been frequently employed for remote communities and when egress routes are blocked. Finally, pedestrian-based evacuations remain relatively rare for wildfire events as they can increase heat-induced risks to evacuees. Other alternative modes of transport, such as motorcycles and bikes, have been used to evacuate quickly and even used during firefighting operations. In our networks review, multiple studies explored road network vulnerability during wildfire evacuation, investigating evacuation path importance, traffic management strategies, and optimizing to reduce congestion and delays, emphasizing the need for adjustments, upgrades, effective evacuation routing, and leveraging GPS datasets to understand human behavior and monitoring route activity during emergencies. Next, evacuation departure curves provided insights into timing and progression of people leaving a specific area during these evacuations, including a sudden surge followed by a slower increase in evacuees during wildfire evacuations. While more research has been conducted on hurricane evacuations, identifying evacuation curves for wildfires remains an open area of inquiry due to their distinct characteristics and behavior. For the planning module, multiple studies proposed strategies for efficient resource allocation. This included personnel, equipment, emergency services. This helps minimize damage caused by wildfires. Moreover, advanced planning and programs such as FireSmart Canada, FireWise in the US, and Community FireGuard in Australia are active and provide recommendations to reduce the risk of wildfires. But participation in these programs is not universal. We also found that locally led initiatives tended to enhance community resilience by involving residents in the decision-making process, thus making it a more proactive process than a reactive one. Moving towards the discussant section, we found one significant gap lies in the lack of comprehensive data on infrastructure damage caused by wildfires. We recommend creating an easy-to-use tracking list to document damages and recovery efforts related to infrastructure. Special attention should be given to potentially flammable infrastructure, and a more comprehensive design and rehabilitation strategy is needed to address the seasonal recurrence of wildfires and its impact on transportation-related infrastructure. Wildfires can cause direct and indirect damage to infrastructure, leading to severe disruptions. So by implementing intelligent transportation systems with sensors for real-time data, we can monitor traffic, damage, wildfire location, and evacuation progress to aid decision-making and post-disaster evaluations. Additionally, hazard mapping and sensing technologies along critical corridors can help reduce infrastructure failures and improve road design guidelines. While private vehicles dominate most evacuations, incorporating multiple modes, including shared mobility and public transit, can significantly improve transportation capacity and provide equitable access for vulnerable populations. Transit-based evacuation planning should learn from strategies used in hurricane evacuations and consider pickup locations and improved public shelters for evacuees. Furthermore, we should consider walking, cycling, water and air-based evacuations. Exploring a diverse range of transportation modes in wildfires can lead to more resilient and efficient evacuation processes. While safety concerns must be addressed, these modes offer flexible and redundant options for evacuees, especially those without access to vehicles or public transit. Rerouting strategies can address congestion and potential exposure to smoke and wildfire heat during evacuations. In our networks discussion, we find that computational models at the local and regional scale should be developed to assist in devising system-optimal rerouting strategies and coordinating traffic with neighboring wildfire-prone areas. Research and agencies should coordinate on data sharing practices and develop departure curves for communities with previous wildfire evacuation experience, which can provide valuable travel behavior trends and insight into when evacuation surges are likely to occur. From a planning point of view, evacuation strategies should be more generalizable and adaptable to varying wildfire conditions across jurisdictions, while actively involving NGOs, CBOs, and underserved populations in planning. Implementing optimized allocation strategies can improve wildfire response efficiency, and communities should draft formal plans identifying shelter locations, relief supply transportation, personnel needs, and wildfire response partners with a focus on equitable service for vulnerable residents. And finally, enhance local capacity through well-researched policies, innovative financial resources, and support from local leadership can help address evacuation challenges and foster collaborative planning between engineers and planners. In conclusion, enhancing wildfire evacuations through transportation engineering requires interdisciplinary research, community involvement, and innovative strategies. We have identified several opportunities for improvement, ranging from embracing multimodal evacuation planning to leveraging technology for real-time monitoring. As we move forward, transportation engineers, planners, and researchers need to come together with community members to address the challenges presented by wildfires. By collaborating and sharing knowledge, we can create more resilient and equitable fire evacuation plans that save lives and protect our communities. As transportation engineers, our dedication saves lives, ensures safety, and upholds the resilience of societies. Thank you all for your time, and I'm happy to take any questions that you may have.
Thank you again for your wonderful work. I'm going to allow other people to put questions in the chat box.